In the infinite quiet of space, where the darkness stretches farther than any human eye can grasp, the solar system appears at first to be a beautifully arranged machine. Planets move in smooth, predictable lanes. Moons follow their worlds like loyal companions. Comets dive toward the sun and retreat with poetic regularity. Even the billions of asteroids scattered across the void seem to obey an invisible blueprint written billions of years ago. Everything flows in one grand, synchronized motion around the sun, spinning in a direction inherited from the swirling cloud of gas and dust that gave birth to all of it. Everything, that is, except a rare and rebellious few. Among the millions of rocks that populate the asteroid belt and the outer regions of the solar system, a tiny number of them break the rules. These asteroids do not move with the cosmic current. They move against it. They orbit the sun in reverse, traveling backward, defying the direction that dominates nearly all other objects in our celestial neighborhood. These strange wanderers travel on paths so unusual that, when astronomers first discovered them, many thought the data was wrong, the calculations flawed, or the observation instruments malfunctioning. But the truth was far more astonishing. Retrograde asteroids are real. They are extremely rare, and they're among the most mysterious objects in the entire solar system. To understand these backward travelers, we have to begin with the origins of the solar system itself. Over 4.5 billion years ago, our sun was just beginning to form from a collapsing cloud of interstellar gas. As gravity pulled this enormous cloud inward, it began to spin. This rotation caused the cloud to flatten into a disk, and everything within that disk, every particle, every grain, every fragment, began to orbit in the same direction. This fundamental spin was inherited by the planets, by the moons, by the comets, and by the vast majority of the asteroids. This shared direction is not random. It is a direct fingerprint of the solar system's formation. It is part of the ancient choreography of creation. But the early solar system was not a peaceful nursery. It was a place of collision, destruction, and violent gravitational interactions. Planetary embryos slammed into each other, creating craters the size of continents. Entire worlds were reshaped by impacts that could melt crusts and vaporize oceans. Millions of smaller objects flew in all directions. Some were ejected into interstellar space forever. Others fell into the sun. Many crashed into forming planets. And some, in extremely rare circumstances, were blasted into reverse orbits. Imagine a young asteroid traveling the normal direction, following the standard path inherited from the rotating disk of dust. Now imagine a catastrophic collision, one so powerful that it shatters the asteroid into fragments, sending debris spinning outward like shrapnel. These fragments, depending on the angle, speed, and timing of the impact, could suddenly find themselves thrown into orbits dramatically altered from their original paths. Some fragments might be knocked inward toward the sun. Others could be pushed out toward Jupiter or beyond. And a rare few might be flung hard enough and precisely enough to send them backward. But impacts alone cannot explain all retrograde asteroids. In fact, they cannot explain most of them. Something far more complicated is taking place, involving gravitational dynamics, orbital resonances, unknown ancient events, and perhaps even the capture of interstellar visitors. To uncover the full story, we must follow these backward travelers through every corner of the solar system, from the chaotic asteroid belt to the distant realm near Jupiter, where one of the most extraordinary retrograde asteroids of all has been found. But before we follow their paths, we must explore what exactly makes an orbit backward and why it is so unusual. Almost all bodies in the solar system orbit the sun in what astronomers call prograde motion, meaning they travel counterclockwise when viewed from above the sun's north pole. A retrograde orbit is one that goes in the opposite direction, clockwise instead of counterclockwise. Retrograde orbits are extremely rare for asteroids. Out of millions of known objects, fewer than 1% travel this way. Yet their existence reveals something profound about the history of the solar system. It tells us that the solar system is not perfectly orderly. It is not a closed system in which nothing unexpected happens. It is a dynamic place shaped by chaotic forces that have left behind a handful of cosmic anomalies. One of the most intriguing retrograde asteroids is 2015 BZ 509. This object does not simply orbit backward. It does so while sharing space with Jupiter, the largest planet in the solar system. And it has done this for billions of years. The discovery of this asteroid shocked astronomers. How could a backward-moving object remain stable near a planet as enormous as Jupiter? Why had it not collided with the planet or been ejected from the solar system long ago? The answer lies in one of the most fascinating gravitational mechanisms that the universe has ever demonstrated: orbital resonance. 2015 BZ 509 is locked in a resonance with Jupiter. This means that despite moving backward, it maintains a stable relationship with the giant planet. It always completes one orbit around the Sun in exactly the same time that Jupiter does. The result is a delicate gravitational dance in which the asteroid and Jupiter avoid collisions through precision timing that seems almost choreographed by nature itself. The existence of this backward-moving companion near Jupiter led scientists to an astonishing hypothesis. 2015 BZ 509 might not be from our solar system at all. It might be a captured object from interstellar space, a cosmic traveler born around another star, swept into our sun's gravitational embrace billions of years ago. If this hypothesis is correct, then 2015 BZ 509 is more than a backward asteroid. It is one of the oldest immigrants in our cosmic neighborhood, older than Earth itself. But Jupiter's gravitational influence has shaped many more asteroids besides this one. The giant planet is the dictator of the asteroid belt. It can attract, repel, capture, and fling objects with ease. A close encounter with Jupiter can dramatically change an asteroid's orbit. If an asteroid approaches Jupiter at just the right angle, its motion can be reversed. This gravitational slingshot effect, common in space missions, can also occur naturally and violently between celestial bodies. Yet even Jupiter cannot explain everything. Some retrograde asteroids reside far from Jupiter, where its influence is weaker. Others move in regions where ancient collisions might not have been common. How do these objects develop backward orbits? Here the story becomes even more complex. A subtle but extremely powerful force, known as the Yarkovsky effect, plays a significant role in shaping asteroid orbits over long periods of time. When an asteroid absorbs the sunlight and re-emits it as heat, the recoil creates a tiny push. This push is incredibly small, but over millions of years, it can alter the orbit significantly, even potentially flipping the direction of motion for smaller or irregularly shaped asteroids. It is a slow, creeping force that can completely transform an asteroid's path without any dramatic collision or planetary encounter. Even more fascinating is the role of chaotic orbital evolution. Over billions of years, small gravitational interactions accumulate. A passing comet, a distant giant planet, a shift in rotation, or even the gravitational pull of neighboring asteroids can alter a path incrementally. Over extremely long scales, these tiny changes can add up to something enormous. They can push an asteroid toward a completely new orbital configuration, including a retrograde one. This slow drift toward chaos is one of the reasons retrograde asteroids act as windows into the deep past. Their orbits contain the imprints of billions of years of subtle, cumulative effects. They tell us what the solar system was like long before Earth stabilized, long before the gas giants settled into predictable orbits, long before the asteroid belt formed in its current shape. These backward-moving objects are, in a sense, relics from an era of cosmic violence. But to grasp the full significance of retrograde asteroids, we must look at them not merely as objects, but as storytellers. Their orbits record events we cannot witness directly. They contain memories of ancient collisions, gravitational wars, and dramatic interstellar encounters. They provide clues about the early solar system that cannot be gleaned from planets or moons. Every backward asteroid is a puzzle waiting to be decoded. In observatories around the world, scientists track these unusual objects with immense precision. They study their motion across the sky, their brightness, their rotational patterns, and their responses to sunlight. They feed this data into powerful supercomputers, which simulate millions of possible past orbits. These simulations reveal when an asteroid's orbit might have changed, which planets it encountered, what collisions it might have experienced, and how stable its current path is. Sometimes the simulations reveal surprising outcomes. An asteroid that today moves backward peacefully might have experienced centuries of violent chaos in the past. It might have been flung inward toward the sun, then out again toward the outer planets. It might have endured a near collision with Jupiter or been part of a massive collision that scattered debris across the solar system. In other cases, the simulations suggest that the asteroid's orbit has always been backward, preserved in a stable resonance since the dawn of the solar system. This means that the asteroid predates many planets. It may be one of the oldest unchanged objects orbiting the sun. The idea that backward-moving asteroids can preserve ancient information has inspired scientific missions and studies. Retrograde objects could help us understand whether the sun captured material from nearby star systems in its youth. They could reveal how common interstellar capture events are. They could show how far cosmic debris travels between systems and how gravitational tides shape the evolution of forming planets. Retrograde asteroids also carry implications for planetary defense. Because they move in unexpected ways, they approach Earth from unusual angles. Traditional tracking models often assume prograde orbits. Backward-moving objects require special monitoring because they can appear suddenly or approach from blind spots. For now, humanity has identified only a small number of retrograde asteroids, but every year, new telescopes detect more. With upcoming observatories like the Vera Rubin Observatory preparing to map the entire sky with unprecedented speed and clarity, astronomers expect the discovery rate to surge. And with each new discovery, the story of retrograde asteroids grows deeper. Some backward-moving objects might hint at unexplored regions of the solar system. Others might reveal the remnants of ancient collisions never before understood. And some may even prove to be visitors from outside our solar system, drifting silently through space until they were caught by our sun. Their backward motion defies expectation. Their origins remain shrouded in mystery, and their journeys tell a story of a solar system far more complex, chaotic, and dynamic than we ever imagined. The mystery of backward-moving asteroids deepens when we examine the intricate structure of the solar system. At first glance, the sun and its orbiting bodies might seem like a neatly organized set of planets and belts, but this is an illusion created by the relative calm of our era. In truth, the solar system is the product of more than 4 billion years of violent evolution. It has been shaped by collisions, migrations, gravitational competitions, and near-catastrophic encounters. Every asteroid that moves backward is a survivor of these events, and each one carries within its orbit a testament to the fierce forces that once dominated our cosmic neighborhood. To understand how backward orbits can exist and persist, we must examine the architecture of the solar system as if it were a layered dynamic ecosystem. At the center lies the sun, the overwhelmingly dominant source of gravity. Around it, the planets orbit in almost perfect synchronization. Between Mars and Jupiter lies the asteroid belt, a chaotic region filled with millions of rocky bodies that never formed a planet. Beyond that reside the gas giants, Jupiter, Saturn, Uranus, and Neptune, whose gravitational influence extends far beyond their physical size. In the deep outer reaches lie the Kuiper Belt and the Oort cloud, enormous reservoirs of icy bodies that stretch nearly to the interstellar medium. Backward-moving asteroids exist within this vast and complex system, and their unusual orbits are the result of interactions that often involve more than one of these layers. Consider the asteroid belt. It is a place of ancient conflict a region that failed to coalesce into a planet because of Jupiter's overwhelming gravitational presence. Every object within the belt is in a delicate tug-of-war between the Sun's pull and Jupiter's disruptive influence. This constant gravitational battle creates areas of stability and instability. In the unstable regions, asteroids can be nudged into new trajectories, flung inward toward Earth or Venus, or cast outward toward the gas giants. A tiny number of these displaced objects find themselves pushed into retrograde orbits, but such shifts require a perfect sequence of gravitational nudges. Imagine a billiard table filled with balls. If one ball rolls across the table, striking another at just the right angle and speed, both can change direction dramatically. But imagine that instead of two balls, there are millions of objects moving at high speeds, with collisions happening for millions of years. In this cosmic billiard game, rare events can turn an asteroid backward. But the asteroid belt is only one arena. Some retrograde asteroids originate in the outer solar system, where the gas giants dominate gravitationally. Jupiter, with its immense mass, acts as both a protector and a disruptor. It shields the inner planets from some incoming comets and asteroids, yet also flings others inward with incredible force. If an asteroid approaches Jupiter on a trajectory that counteracts its existing motion, the planet's gravity can slow the object enough to reverse its orbit. This process is rare, but it has been observed in computer simulations and is one of the likely explanations for several backward-moving objects. One of the most revealing insights into retrograde asteroids comes from studying gravitational resonances. These are natural frequency matches between the orbital periods of two celestial bodies. When an asteroid enters a resonance with a planet, it may remain locked in position relative to that planet, even if its orbit is highly unusual. In certain cases, a resonance can stabilize a retrograde orbit that would otherwise be too chaotic to last. Such is the case with 2015 BZ 509, the asteroid whose backward orbit around Jupiter defies expectation. Scientists discovered that this asteroid occupies a 1:1 resonance with Jupiter, meaning it takes the same amount of time to orbit the Sun as Jupiter does. Despite moving in the opposite direction, it never collides with the planet. Most astonishingly, simulations suggest this asteroid has been in its backward orbit for billions of years. This level of stability implies that it may have been in its retrograde path since the solar system's earliest era. If so, it offers a unique look at processes that took place long before Earth formed its oceans and atmosphere. The idea that 2015 BZ 509 could be an interstellar capture adds a layer of intrigue to an already extraordinary object. The early solar system existed within a stellar nursery, a region where many young stars were born close together. These newborn stars often pass near each other, their gravitational fields interacting. During this era of close encounters, it would have been possible for the Sun to capture material from nearby star systems. If any of this material settled into stable orbits around the Sun, it might have remained untouched for billions of years. Retrograde objects like 2015 BZ 509 could be remnants of these interstellar exchanges. But retrograde asteroids are not limited to the vicinity of Jupiter. Some move backward in the inner solar system, crossing the orbits of Earth, Venus, or even Mercury. These objects are particularly difficult to track because their reverse motion makes them appear to move in unexpected patterns across the sky. A backward-moving asteroid might seem to jump erratically from night to night, confusing early observers before modern software became sophisticated enough to predict such paths accurately. One such object is asteroid 343158, a near-Earth asteroid with a highly tilted and backward orbit. Its origins remain uncertain. It may have come from the outer solar system and been pulled inward, or it might have originated in the asteroid belt and undergone a complex series of gravitational interactions that reversed its motion. Its current path could bring it into close approaches with Earth in the far future. Those simulations show its orbit is highly chaotic and difficult to project beyond a few million years. Retrograde asteroids that cross Earth's orbit hold particular interest for planetary defense because they approach Earth at higher relative velocities than prograde objects. They carry more kinetic energy. Even a small retrograde asteroid could cause significant damage if it impacted Earth. Moreover, their reverse motion makes future paths harder to predict, especially over long periods. Modern planetary defense systems must account for these unexpected motions, demonstrating that retrograde asteroids are not merely scientific curiosities. They represent real and complex challenges. Beyond gravitational interactions, the long-term evolution of an asteroid's orbit can be influenced by forces more subtle than collisions or close encounters. The Yarkovsky effect, for instance, slowly alters the trajectory of rotating objects. Imagine an asteroid spinning as it travels through space. One side heats up in sunlight and later releases that heat in the form of infrared radiation. This release of energy produces a tiny thrust, barely noticeable in the short term, but immense over millions of years. The effect can push an asteroid inward or outward. For certain shapes and rotations, it can even alter the orbital inclination, gradually tilting the orbit until the asteroid flips direction. Though rare, these scenarios highlight the profound impact that sunlight can have over geological timescales. Chaotic evolution plays an even larger role in shaping retrograde motion. The solar system is not a perfectly stable system. It is influenced by the tiniest changes in gravitational forces, which can accumulate unpredictably. A distant passing star, a shift in a planet's orbit, or the long-term wobble of Jupiter's path can all create ripples that affect asteroid motion. These ripples, though small, can accumulate over billions of years, producing outcomes that would seem impossible on shorter timescales. A prograde asteroid might drift into a resonance that destabilizes its orbit, sending it into a new path that eventually becomes retrograde. This chaotic evolution means that retrograde asteroids do not simply tell the story of ancient collisions. They also reveal the ongoing evolution of the solar system. They are evidence that even on timescales of billions of years, the architecture of our cosmic neighborhood is not fixed. It changes, shifts, and transforms in response to tiny forces acting continuously over immense spans of time. When astronomers observe a retrograde asteroid today, they are not simply looking at a rock traveling backward. They are observing the result of billions of years of cosmic history reshaping itself. Every backward orbit is a frozen record of the past, a relic that tells a story of improbable events and delicate gravitational interactions. The importance of studying these objects goes beyond curiosity. Understanding retrograde asteroids helps scientists refine models of solar system evolution. It helps researchers trace the paths of ancient collisions, identify potential interstellar capture events, and map the long-term gravitational interplay between planets and smaller bodies. Retrograde objects challenge our assumptions, forcing us to acknowledge that the solar system is far more dynamic and unpredictable than once believed. But to fully appreciate the significance of retrograde motion, we must zoom out even further. We must look beyond individual asteroids, beyond the asteroid belt, and beyond the influence of Jupiter. We must examine the gravitational environment of the solar system as a whole and how its past interactions with neighboring stars might have shaped these backward-moving objects. In the earliest days of the Sun, our star was part of a dense stellar nursery, a region filled with other young stars forming from the same cloud. These stars were born close together, sometimes separated by just a few light years. Over time, they drifted apart, but in the beginning, their gravitational fields overlapped. During this era, the Sun could have easily captured objects from neighboring stars. If those objects entered the solar system at unusual angles, they might have settled into retrograde orbits. If so, some backward-moving asteroids may be older than the planets themselves, fragments of rocky material that originated around entirely different stars. If backward-moving asteroids are interstellar captures, they could carry clues about the composition of other planetary systems. Their mineral content might be different from objects native to the solar system. Their isotopes might have unusual ratios, providing a chemical fingerprint that reveals their alien origins. Future missions to sample such objects could uncover things never before seen in local asteroids. This possibility excites astronomers for another reason. Discovering interstellar material within our solar system could help us understand how frequently stars exchange debris. If interstellar captures are common, then planetary systems might regularly swap material, potentially spreading the building blocks of life over enormous distances. Retrograde asteroids could be evidence of an ancient form of cosmic interchange that shaped the chemistry of planets, moons, and perhaps even early life on Earth. But confirming these theories requires detailed observation and simulation. Scientists must trace backward the orbital history of retrograde objects, reconstructing their paths over millions or billions of years. Doing so challenges even the most advanced computational tools, because the orbits are so chaotic that tiny errors can produce wildly different results. Yet with each attempt, astronomers learn more about the forces that shape these orbits and the possible origins of these remarkable objects. While the scientific implications are profound, the narrative of retrograde asteroids also reveals something philosophical about the universe. It shows that order and chaos coexist. It shows that even in a system governed by physical laws, rare anomalies emerge that defy the dominant patterns. It shows that nature allows for exceptions, for outliers, for rebels that follow their own paths. Backward-moving asteroids are the rebels of the solar system. They travel against the current. They defy the inherited motion of the sun's spinning disk. They take paths that almost no other objects take. And their existence reminds us that cosmic history is not a single smooth progression, but a chaotic symphony of events and forces interacting over unimaginable timescales. Some retrograde asteroids will eventually be ejected from the solar system. Others will collide with planets or crumble from gravitational stresses. But some will survive for billions of years, continuing their backward journeys long after the planets have shifted into new positions. They are, in a sense, immortal travelers through a constantly changing cosmic landscape. Their story, however, is far from complete. Each new discovery raises new questions. What unseen forces shape their paths? What collisions or interactions reverse their orbits? How many more retrograde objects remain undiscovered, especially in the far reaches of the Kuiper Belt or Oort cloud? Could some of them hold clues to the earliest building blocks of the solar system, or even to material originating outside it? To answer these questions, we must continue to explore deeper, farther, and with more powerful tools. The solar system we know today is calm only on the surface. Beneath its quiet motions exists a slow and continuous reshaping that has gone on for billions of years. To understand why some asteroids move backwards, we must immerse ourselves in this hidden architecture built not by hands but by gravity, collisions, and time. In this part of the documentary, we step deeper into the regions where retrograde orbits are born and preserved. These regions hold invisible borders and gravitational landscapes that carve the pathways of small bodies, guiding them into strange journeys that defy the original. Rotation of the solar system. Imagine drifting away from the inner planets where sunlight glows like white fire and moving into the domains where the light begins to thin. Gravity becomes a sculpture of slopes and curves. Even the space between planets behaves like a terrain, with hills that pull objects inward and valleys that guide them along predictable routes. But hidden among these predictable routes are chaotic zones where the faintest push can flip an asteroid's direction. These zones are where the most interesting stories of retrograde asteroids begin. One of the primary sculptors of retrograde motion is Jupiter. In many ways, Jupiter acts like a cosmic bouncer, guarding the inner solar system from intruders. But its gravitational field is not just a shield. It is a vast landscape of traps, resonances, and escape routes. When a small asteroid wanders too close to Jupiter, its orbit becomes vulnerable to dramatic transformation. Some are slingshot into deep space. Some are flung inward toward the sun. Some are broken apart by tidal stress. And a rare few are flipped backwards, entering a retrograde orbit that can remain stable for astonishing lengths of time. When scientists simulate these interactions on supercomputers, a pattern emerges. An asteroid may begin in a gentle prograde orbit, but then slowly drift due to sunlight pressure or minor gravitational nudges. Once it reaches the boundary of a major resonance with Jupiter, chaos begins. Inside a resonance, every orbit of the asteroid matches in rhythm with Jupiter's movement. These synchronized cycles can amplify small changes. A tiny adjustment becomes magnified over hundreds of thousands of years. In some cases, the oscillation becomes so extreme that the asteroid's orbital inclination tilts dramatically, lifting it far above the planetary plane. Another shift can then cause the orbit to invert entirely, turning a prograde asteroid into a retrograde traveler. This may sound like a dramatic and sudden event, but in reality, it occurs slowly over millions of years. No explosion is required. No collision is required. Only gravity and time. The asteroid steadily crawls across a gravitational landscape that eventually folds its path inward. By the time the reversal is complete, the asteroid has been sculpted into a relic of the past, moving against the grain of the sun's original rotation. One example that has fascinated scientists is the asteroid known as 2015 BZ 509, also called BEAST. This object orbits the Sun in the opposite direction to Jupiter despite occupying the same orbital path. It is astonishing because such an arrangement should be unstable, yet simulations show it remaining secure for at least 1 million years and possibly for much longer. Its movement is a delicate dance where every backward step is counterbalanced by Jupiter's forward motion. It circles the Sun backwards while weaving in and out of Jupiter's path, like two dancers performing opposite steps on the same stage. The existence of BEAST raised an important question. Did this asteroid form in the early solar system and later become retrograde through gradual gravitational shifts, or did it arrive from outside the solar system altogether? The second possibility is far more dramatic. If BEAST is a captured interstellar visitor, then it represents a piece of another system's history preserved inside ours. It would be a fossil from beyond the Sun's birth cloud, trapped by gravity and inserted into a stable backwards orbit through an extraordinary chain of events. Whether or not BEAST is truly interstellar, its behavior demonstrates something deeper. Retrograde asteroids are not accidents. They are products of a dynamic system that continues to evolve. They reveal that the solar system is not a frozen clockwork machine, but a living network of gravitational influences. Every planet, every minor body, every grain of dust contributes to the overall symphony, and sometimes the harmony of thousands of prograde objects makes space for a rare and beautiful discordant note. To truly grasp the complexity of retrograde motion, we must consider the architecture of the solar system as it was billions of years ago. Early on, the giant planets were not in their current positions. They migrated outward and inward as they gravitationally interacted with the disk of gas, dust, and smaller bodies. These migrations created enormous waves of instability. Asteroids and comets were tossed into new orbits, some thrown toward the sun, and others flung into distant regions. During these upheavals, the seeds of retrograde orbits were planted. When multiple planets shift positions, they reshape the balance of forces that small bodies experience. Many early asteroids were swept up into resonances or thrown into unstable zones where their orbits were twisted, elongated, or inverted. Some scientists propose that entire populations of retrograde asteroids may have formed during these chaotic migrations. When the giant planets shifted, the gravitational environment of the solar system changed dramatically. Older families of asteroids that once traveled in the same direction as everything else might have been jolted into new paths. Some survived the turbulence by settling into retrograde orbits that were later stabilized through resonant interactions. Another point of interest comes from the outer solar system, where the orbits of distant comets and small bodies often show a wide range of inclinations. In this region, the influence of the Sun is weaker, and the gravitational pull of passing stars and the Milky Way's tidal forces becomes more relevant. Over long timescales, these subtle interactions can tilt orbits to extreme angles, including retrograde. These bodies then migrate inward over millions of years, eventually appearing as retrograde asteroids when they enter the inner regions. Researchers have identified numerous small bodies whose orbits trace back to the Oort cloud, the distant sphere of icy objects that surrounds the solar system. These bodies were likely disturbed by passing stars or slow gravitational tides and set on long journeys that eventually brought them inward. As they fall from the outermost regions, some pass close to planets that further modify their paths. A single encounter with Jupiter or Saturn can shift their inclinations by tens of degrees, turning them into retrograde interlopers in the inner solar system. Retrograde asteroids also provide important clues about the long-term stability of our planetary system. Simulations that incorporate backward-moving objects reveal how the gravitational web adapts and responds over time. Some retrograde orbits are surprisingly stable. Counterintuitively, an asteroid moving against the direction of the planets may actually avoid collisions more effectively because it passes the planets at high relative speeds, spending very little time in the same region of space. These brief encounters reduce the cumulative gravitational nudges that normally destabilize prograde orbits. As a result, some retrograde asteroids can remain in their unusual motion for millions or even billions of years. This stability also creates opportunities for future research. Retrograde asteroids offer a unique window into the early solar system because they may avoid the same collisional processes that shaped other families of asteroids. Many prograde asteroids have been smashed, fractured, and reshaped through countless impacts. Retrograde asteroids, by contrast, might have remained relatively untouched. Their surfaces and internal structures may therefore preserve information about the early solar system that has been erased elsewhere. Understanding retrograde objects also illuminates potential future hazards. While most backward-moving asteroids are harmless, their unusual velocities mean that if one were ever put on a collision course with Earth, the impact energy would be immense. A retrograde object striking Earth head-on would approach at far higher speeds than a typical prograde asteroid, delivering significantly more destructive force. Fortunately, such objects are rare, and most retrograde orbits are stable, but studying them helps scientists refine models of future impact risks. Beyond their scientific importance, retrograde asteroids also challenge our imagination. They represent the exceptions, the outliers, the travelers that move against the prevailing direction of the solar system. Their existence reminds us that the universe is not rigid, but full of possibilities created by time, chaos, and chance. They invite questions. How many more exist that we have not yet found? How many might be interstellar captives? How many might hold ancient material untouched since the dawn of the sun? As telescopes grow more powerful and surveys more comprehensive, new retrograde bodies are being discovered. Each new find brings us a step closer to understanding the full story of how these strange orbits come to be. Astronomers now monitor regions of the solar system once considered empty, revealing faint objects that blur the boundaries between asteroid, comet, and interstellar fragment. The more we look, the more we realize that the solar system is not uniform. It is filled with diversity, complexity, and mystery. These backward travelers form a small but significant part of that mystery. They are the solar system's rebels, defying the direction established by the rotating nebula that birth the planets. But they do not defy physics. They reveal the deeper truths of gravitational evolution. They show that direction is not destiny, and that even in a system guided by order, chaos plays a fundamental role. Retrograde asteroids are the footprints of that chaos. In conclusion, the retrograde asteroids are the solar system's quiet rebels, moving backward through a universe that mostly turns the other way. They are born from ancient collisions, violent planetary encounters, chaotic migrations, and perhaps even distant stars beyond our own. Their strange paths remind us that the solar system is not a perfect clockwork machine, but a living, evolving structure shaped by time and gravity. By studying these backward travelers, we uncover forgotten chapters of our cosmic history, gain insight into the forces that shaped our worlds, and open the door to mysteries that still wait in the dark. Their motion may be rare, but their story is essential, and their existence proves that even in the vast order of the cosmos, the unexpected always finds a way.